Okay, thank you, everyone. My name is Joe Santanello. I'm at NASA Goddard in Hydrological Sciences. I'd like to thank the organizers for inviting me to speak, and for my collaborators in GWEX Glass and the Loco working group, and also the PBL study team that just wrapped up. So what I'm going to talk about today is really how I became interested in boundary layer observations via the lens of land-atmosphere interactions. So I'm going to talk a little bit about first our land-atmosphere coupling, local land-atmosphere coupling initiative under GWEX, over a decade old now. Just a primer on that. What kind of metrics we've developed, what kind of model development it enables, and what kind of science it enables. And what's the importance of boundary layer within all of this is what I'll pivot to, and what NASA is doing from a spaceborne perspective to address these challenges. So the origin story of Loco is that it was motivated by the Glacé study of Randy Koster in 2004, where they showed coupling hotspots in model world that connected soil moisture to precipitation. What our Loco group and interest realized was that this is a model world result, and you can't apply observations to it necessarily, this omega metric. And we really want to understand the processes that connect soil moisture and precipitation, not just the endpoints themselves. And so what we came up with, what we call a Loco process chain, is can we explain the physical mechanisms that lead to coupling strength differences? Are there observable diagnostics or metrics that we can develop that can quantify the role of land-atmosphere coupling? So what we did was we essentially broke down the sensitivity of precipitation to soil moisture into how sensitive are fluxes to soil moisture, surface fluxes, and then how sensitive is the atmosphere, if you will, to those fluxes. So you have sort of two legs here of the terrestrial feedback, terrestrial sensitivity and an atmospheric sensitivity. And so we developed this process chain paradigm, which is simple and not all-encompassing, but it's a starting point. It's some way we can wrap our heads around the complexity of land-atmosphere interaction. And it basically describes how soil moisture influences surface fluxes, how that influences the PBL, how that then influences entrainment feedbacks onto ambient weather, and then ultimately how this all cumulatively affects clouds and precipitation. So this is really the paradigm we work under. We try to understand these links in the chain and the feedbacks that are inherent between them. So as mentioned, you can also break this process chain down into a terrestrial leg of just the surface sensitivity of fluxes and soil moisture versus how the atmosphere responds to those sensitivities. And so you'll see this paradigm in Paul Diermeier's papers and others in the Loco group, of the two legs of coupling, if you will. So what kind of metrics have we developed in resources? Well, first off, the goal of these metrics is to synthesize some of these processes and feedbacks. It's complicated, as Mike Eck has shown, probably not the only time you'll see this diagram during this workshop, but it's very complicated. And we need to boil it down into something that we can quantify and observe and apply to our models. So that's really what the goal of these metrics are, is to synthesize various parts of this. And again, we have our process chain here, as outlined before. Each of the metrics that we've developed here, highlighted in different bubbles, basically addresses different temporal scales here and different vertical scales of coupling. So you'll see mixing diagrams here are really diurnal cycle based in terms of hours, and they encapsulate surface fluxes, PBL properties, and connective initiation. Some of the other ones focus more, again, on the terrestrial leg only, like soil moisture memory is on the order of days. It has to do with surface states. And then some of these others are more climate-driven or annual cycle-driven temporally, but they encompass everything from the surface on up. So each of our locometrics are either process-based or statistical, and they encapsulate different parts of the process chain, essentially. So we have these cheat sheets with all our locometrics here that bite off different parts of this chain, and the cheat sheets show you what input variables you need, what are the temporal and spatial scales they can be applied to, if they can be calculated from observations. So this column here, you can see, are all yeses. And that's by design, except for the Glacé metric. All of these are observable metrics, and that's a key if we're going to make progress on model development. So I'm going to flip through this slide rather quickly, but you can pause the recording. Basically, this is describing how we can apply our metrics at different resolutions, whether it be global, GCM scale, at point scale, which is really the RMSGP site, for example, or the mesoscale in between. And there's pros and cons of each in terms of what observations you have at each scale, what kind of models they can be applied to, and what understanding you get out of them. So our working group of Loco, again, more than a decade old now, the charge is really to understand, quantify, model, and predict the role of local land-atmosphere coupling. And the goals the last 2 years have focused on improving observations, because without observations, we can't apply these metrics globally, of course. So a lot of this has been focused on PBL observation improvement. We want the operational NWP and climate centers to adopt these metrics in their development rather than just one-at-a-time evaluation of what's going on in their models. They need an integrated process-level approach. And expanding the scope and reach of Loco, really the science of Loco and the metrics, beyond just water and energy cycle, warm season, thermodynamics, and beyond a single column assumption. So we're trying to expand that process chain paradigm. And these are our members currently in the Loco group. So we do have resources in terms of GWEC's GLASS website with the Loco page, which has a lot of information and publications, all listed there and up to date, so I would point you towards that. More importantly, we have our BAMS review article on Loco from June 2018. That is a full primer of everything Loco, the motivation, the metrics, the applications. So strongly recommend checking that out if you're interested in more details. And we have a coupling metrics toolkit, which is being, it's already coded up in Fortran, but also being coded up in Python currently, where we have a subset of Locometrics that are already ready to go off the shelf for your particular need. So what have we done with these metrics? Again, a flavor for things we've done at Goddard are to apply these metrics to our new WRF, NASA WRF system and land information system to really help quantify the impacts of various things such as irrigation, new irrigation schemes in the model, to intercompare reanalyses, to look at how initial conditions of soil moisture impact NWP, to look at how land model calibration or assimilation impacts land-atmosphere coupled prediction. So these metrics can be applied across the board to model development and different types of models as well. And we have an example of this tomorrow in the poster session where Tricia Lawson-Parker and I have and Sujay Kumar have our paper that is in the last stage of revision, hopefully, but you can get a preview of it tomorrow. And it really focuses on using new observations of the process chain, including the PBL, to calibrate land model parameters and states and see how that influences coupled prediction. So instead of just calibrating a land model offline in a traditional sense, we can now calibrate atmospheric variables as well and see where the links in the chain, the process chain, are tightened and where they're loosened, where do improvements happen versus degradation by introducing a new observation into that process chain. So I recommend checking that out. So to the end of observations. The importance of PBL observations has become apparent since Loco was initiated because, again, we have all these metrics, which you've seen here, that cover various parts of the process chain. And what's at the heart of it is PBL properties. PBL is the interface for the surface to interact with the atmosphere. So those observations are key to many of these metrics. And this table here summarizes what observations are necessary for different diagnostics here in terms of temperature and humidity profiles in the PBL, near surface quantities, or boundary layer height. So which of these metrics require which of these boundary layer observations types? And you can see it's quite a bit of need here. So if we improve our boundary layer observations, whether it be from ground-based networks, such as being discussed here with Ameriflux, or from space, it's going to greatly enable our use of these metrics with observations to evaluate and help further develop and improve models. And to that end, there was a UFS land modeling workshop last week where they shared this slide, which says these are the top forecast concerns that they've received. And number one is boundary layer profile, stability, and surface temperature. So it doesn't get any more land-atmosphere interaction and PBL focused than that as the number one need in terms of model development. And so these observations are critical not only to our research, and we like local science, but also the operational communities. So what are we doing in that regard? Where do we have observations such as those? Well, single sites usually to this point. Super sites like the RMSGP is the only one in the US that has for a long record length of all these process chain variables. So a lot of work has been done there, a lot of publications necessarily, and we're very grateful to DOE for supporting this site and continuing to support this site. And you've heard earlier a lot more details about the instrumentation there. In 2015, we launched a campaign on 12 individual days with hourly radiosondes. So the key here is this is available on the ARM data discovery, and it's a great data set that could be used by this community to see what if we did have Ameriflux sites with boundary layer height all the time. What could it enable? Well, you could use this as an example of what boundary layer data could enable, because we have 12 days with amazing temporal resolution of radiosonde data. So just a short plug for that data set there. Also, the LAFE campaign over the Southern Great Plains was in 2017, led by Volker Wolfmeyer, and there's a BAMS article summarizing this campaign. But it really is another example of a super site, a land atmosphere super site that has all the variables you need from soil moisture on up to address these feedbacks in a comprehensive way. And also a look to the future in this article, the BAMS article, about the GLAFO concept of a land atmosphere feedback observatory that we will need going forward to really address a lot of the science needs. And again, that has to do with co-location of these observations in a routine sense. So what do we have now? Just global radiosonde networks. Of course, we have ground networks as well, profilers, but for a long time we're reliant on the synoptic sondes, which just aren't enough. It's only twice a day with bad daytime sampling, especially over the US. What do we have from space? Well, we're doing a lot of monitoring from space of Loco variables. That includes soil moisture and hydrology here with all these missions. This is a not exhaustive list as well. And we're doing well in the atmosphere in terms of mid to upper troposphere, precipitation, clouds, aerosol, and chemistry. But obviously what's missing here in our observations is the PBL. So there's a PBL gap from space. And it is now being recognized, and there's action being taken by NASA and the community to address this gap, which is great news. So what is that action? The Decadal Survey came out in 2017, which gives direction to NASA for the next decade. And they identified that temperature and humidity profiles and boundary layer height are high priority incubator measurements. They're high priority because they recognize that PBL is important for nearly all the panels of weather, climate, hydrology, ecosystems, and applications, which is unlike any other measurement that was recommended. And it's also an incubator measurement because it's so immature, it's a hard problem from space to get the PBL. If you think about it, just spatially, you're farthest away from the PBL when you're in space, you're closest to it when you're on the ground. So this is a hard problem. It's going to take time to incubate or develop approaches to do it from space. So that's what that means. And another thing to notice, the community and land atmosphere community has really buoyed this because we've submitted white papers. A lot of people have written manuscripts that highlight the importance of boundary layer information for land atmosphere science. And because of that, in 2007, the Decadal Survey didn't mention PBL at all. And 10 years later, because of the rallying cry of the community, it's mentioned 129 times, as well as a high priority measurement, which means that NASA will invest in it and already is investing in it. So how are they investing in it? They launched the PBL incubation study team in FY20. We just wrapped up. I was part of this team and delivered our white paper to headquarters. That will help them formulate a roadmap for PBL incubation going forward over the next 10 years. How do we get something to space? We have to develop the technology. We have to outline the science needs and do both at the same time. So again, it's a hard challenge that will take time, but NASA is dedicated to it. Check out this website here for the white paper and further information on what the study team did. And we also have had workshops, 3 of them in the last few years, and AMS and AGU sessions on PBL from space. So we're really looking at community outreach because it's going to take everyone and everyone's expertise and input to help us win a successful strategy for spaceborne PBL measurements. So a sneak peek of the white paper, and again, this is publicly available. There's a lot in here on science and technology that I think would be interesting to this group. There's also a lot of discussion of ground-based networks and their role, as well as airborne measurements. So you can peruse this. There's an executive summary that's only 2.5 pages. I highly recommend reading that and then seeing where it takes you after that. There's also a roadmap that headquarters may or may not follow, hopefully follows to some degree, for developing the science over the next 10 years and the technology over the next 10 years. And you'll see here PBL community meetings every 2 years at least to make sure we have that community engagement, and they can help steer as this evolves, because not every path will be the right path and we'll have to change course a little bit probably. So we're going to keep after that. So in terms of the science, which is probably why a lot of you are here in this workshop, there's a lot of science in that white paper. And PBL is broad and difficult, so it was not easy to synthesize PBL science, but this is our stab at it. And basically, it comes down to 4 major themes, as you can see here. And one of them is PBL and surface interaction. And there are subsets of questions that are posed about the importance of PBL measurements to advance this science. You can take a look at the rest of them here as well. Modeling, mixing, and air quality is certainly relevant to this group as well. So I have all the charts here. This is from the white paper, but we'll skip through to G3, which is PBL and surface interaction. And so you can see these questions here. A lot of them look familiar to some posed by Ameriflux or by DOE and by others, by NOAA. But what this Science Application Traceability Matrix, SATM, tells you is, what are your goals? What are your questions? How do you answer those questions? What do you need to measure? Okay, so this is a key column here. And then how do you do those measurements from space? And this is where the incubation needs to take place for technology. But we also need to better define what we need, as a laundry list of variables to do our science. And so you can see for land, particularly relevant here are synergistic measurements such as surface properties. You can't just do boundary layer T and Q or boundary layer height. You also correspondingly need these other measurements. So we can't avoid that going forward. So there will be a role for ground-based and spaceborne measurements regardless going forward. So I'll flip through these and then get to some more of the white paper, which is could be of interest to this group, which is the program of record chapter. What this means is what's flying now in space, what can it tell us about PBL, how good is the data, what are the resolutions, and what can it tell, what it cannot tell us as well. Because this hasn't been mined nearly enough. We have a lot of things flying now that gives us little bits and pieces of PBL, but it could be mined a lot more for the science that we're doing. So I would motivate this community to look at this chapter and think about, I didn't know, you could use this data to get boundary layer height or CAPE or, profiles, things like that. So this is somewhere for this community to look to see what they can mine while we're waiting for the next generation of sensors, which will take, a decade. So we don't want to just sit around and wait, have the science stall. We want to make sure we're using everything we can. And that includes ground-based networks. So program of record includes ground-based networks as well. So these are the specific recommendations that the white paper went through. I'm not going to go through all of these, but just to give you a flavor for the different types of active and passive instruments of an observing system that we've recommended. And it will take an observing system to put all these pieces together. So these are from different instruments, slicing the PBL here in the lower layers. And no one instrument can do it well by itself, so it is going to take the combination of them. So what's next? NASA will release a solicitation imminently that will be due in 3 months to support 3-year projects on PBL incubation. That includes science, remote sensing science, and modeling probably, and technology. We're not sure of the details yet, but we're waiting anxiously. So keep an eye out for that. And then they'll repeat that 3 years from now to support more projects or continued projects. I said community engagement is critical as we go forward. And this PBL challenge is incredibly broad and complex. And it will take an observing system that does include ground-based, airborne, and spaceborne measurements. The novel challenge is how to put these pieces together to something that will kind of transform our science and address these complex needs. So, just to wrap up with some thoughts about challenges and outlook. As I said, the white paper emphasizes suborbital and ground-based networks as well, so take a look at that. Look for that language in the white paper. It's not simply just to cal-val new spaceborne instruments like in the past. We need multi-sensor synergy of measurements, spaceborne just being one component. So we have to think novelly about it going forward. And don't forget, ground is closest to the PBL. Why make the problem harder and start from space? We need the ground-based networks. And it will be a challenge to work because different agencies support different types of technologies. You know, NASA wants to fly to space. Other agencies are quite content supporting ground-based, so we need that collaboration. And this focuses on T and Q profiles and boundary layer height, but there are lots of other aspects to PBL like winds, chemistry, aerosols, air quality. PBL incubation will include those components as well in terms of the science and applications. So keep that in mind. And then discussion topics. What types of resolution of boundary layer observations from space would be most beneficial to you? I say, quote unquote, you in these diverse communities. This information is going to be important for NASA to consider, so we're open to this feedback. Likewise, how impactful would a boundary layer height product by itself, without the profiles of T and Q, be? Is that something valuable that you could immediately use in your research? And how can we use PBL observations to bridge community divides? And I think we'll talk about this in the breakout, but we have very distinct communities here, interdisciplinary communities with different backgrounds. And so my last point here is that, again, the complexity of land-atmosphere interactions is a challenge for scientifically because we have different people in the room. We have atmospheric scientists here who look at all of this as boundary condition, right? Traditionally speaking, not necessarily the ones at this workshop, but others. Likewise, we have hydrological communities that look at all of this as forcing onto their models. So we have to think about both sides of the fence. And here being that fence where we can't just simply pass fluxes to the atmosphere and call it a day. We have a diverse background in our Loco group, you can see here, coming from a wide range of backgrounds and expertise. And something I realized about 7 or 8 years ago when I presented this to ASR meeting actually, was that a lot of atmospheric or meteorologists end up doing land surface modeling or hydrology, much less so vice versa. That was my perception of things. I didn't have hard data on it other than to look at the Loco working group. What does that mean? That means you have a better chance of the land community understanding the atmosphere than vice versa. So this is important in a field like ours because we need to be able to communicate best, and it's best to communicate when you know other strengths and weaknesses. And so I got some hard data from this workshop, which I'll wrap up with here, that they asked you to check a box when you registered or submitted an abstract. And they asked, do you want the land side of land atmosphere or atmosphere side? And I thought that was interestingly posed because my natural instinct is both, and many others are as well. But I was curious to see the data on what people check, because you can choose both. You don't have to choose one or the other. And so here are the results. Atmosphere side only, not land, 88. Land side only, not atmosphere, 21. And then both sides, 87. So this actually backs up this notion that you don't have many people doing land that don't know the atmosphere or something about the atmosphere. You have many more atmospheric scientists that don't know much about the land. So we can debate this, but I think this is statistically significant. And I'll end on this note, and thank you for your time.